introduced an awful lot of apparatus. Not shown that many numerical results. So I wanted to finish off by showing how some of this apparatus works out. In the case of the periodic cube, this is very largely based on a paper by John Gregorian in 2021. Before we get going there, I'm going to give you an outline of a technique for solving initial value problems. The traditional way of doing it is doing it in frequency space via apparatus of Landau that I haven't talked about. But John's paper from 2021 uses a technique solves the equations, linearized conditional response field equation in the time domain, and he's working on a paper which describes a general apparatus, and I think it's worth just describing that general apparatus, and then in the periodic cube you will see a concrete example of its working. So the linearized CBE is this, right? Here we have the first order terms of the conditional response field equation. And the thing is that these two terms taken together make the total derivative of the perturbed distribution function along unperturbed orbits. So the idea is that what we do is obtain F1 by integrating it along the unperturbed orbits. So that's what this equation says. This equation says that the perturbation at the base point W at time t is the perturbation that there was at Wi, initial time ti, plus the sum of the changes which have occurred on the way. This, since h0 depends only on, since h0 depends only on position because it's phi 1, that's what this reduces to. That's what this reduces to. Okay, so we want to know what the density is associated with this. So we integrate over velocities, and also this is the potential created by whatever density we arrive at. And so we so this integral over velocities. This gives the perturbed potential. Here is this derivative dvx. Here's the f0 by dv, and this integral over velocities is associated with this integral over velocities that we have done in order to get the density at time t. And we're still integrating into t prime. So the order of integration of the velocities in t prime has just been reversed. That's basically all that's happened. And that this equation can be written in this form, where this is a kernel. So this kernel depends on the unperturbed distribution function, and that's it. It's a slightly subtle kernel because it involves this integral over velocities. And these velocities are the velocities at the current time t. They're not the velocities at either t prime or, well, x double prime is just a dummy variable that's introduced to this state. It doesn't have any particular time associated with it. But it's important to remember that this velocity you're integrating over is not the velocity associated with x prime. It's the velocity associated with x. And I think maybe we have a sign problem here, but that's... So, equations of this type, right, this is a threshold integral equation, are very easily integrated numerically, and people have at various times done that. So, for example, an early example in stellar dynamics where this is done is in the classic paper of Julian and Toure, 1965 or something. Anyway, in the 1960s, before there's any sort of abstract apparatus, they basically formulate an equation like this and integrate it, and it makes the problem extremely tractable. Okay. So in terms of potential density pairs, it looks like this. Remember, we introduced basis functions phi alpha and rho alpha, and you had that rho was the sum of A alpha, phi alpha, and you had that phi was the sum of A alpha, phi alpha. So once you know the A alphas, you know pretty much everything. So this equation takes the equation we've just been looking at could be considered to be an integral like this, and it turns out that you can obtain this kernel. There's a very straightforward procedure for obtaining this kernel, tabulating this kernel. For every pair of values alpha and alpha prime, you do some integrations. You integrate backwards in time actually from t, and that enables you to assemble this kernel through this formula here. It's a very neat kind of apparatus, and once you've got this thing tabulated, you can solve for the linearized response to any system. B alpha here is the B alpha are the expansion coefficients of whatever is driving the fluctuations. Okay, so that's just a general way of solving the linearized Cauchy-Boltzmann equation that will be used in this scientific model with periodic cube. So we take a box of side L and we impose periodic boundary conditions on potential and also on the motions. We need a curly L, script L, L over 2 pi, and then if we define theta to be 2 pi x over L, then, or which is the same as x over L, then theta has the status, turns out, has the status of an angle variable. So if theta increases by 2 pi when x increases by L, so it's when you go across the box, and the principle we're going to operate on this is that the particle goes out at one side of the box, it comes in again magically at the corresponding periodic point on the other side of the box, and so these theta variables get to be periodic. And then the momentum that's canonically conjugate to this, if you bother to write down just a generating function for canonical transformation, you can easily show that it's this animal here, in other words, L times V. So V is J over L, and X is L theta. Very straightforward. The relationship, so obviously it's natural to Fourier transform the density and the potential inside this box. So we're going to have discrete Fourier transform coefficients phi k, where k is a vector made of integers, and it's easy to show that the Poisson's equation means that they're related to each other by this very simple formula here. So if you want to know what the potential is, it's incredibly simple. You just Fourier transform the density divided by k squared multiplied by this constant, and there you are. A tiny bit more work is involved to show that suitable potential density pairs are these things here. So here is a potential. It clearly has the dimensions of a potential, and because k is an integer, k is the modulus of vector k, and the corresponding density is this. In other words, if you take del squared of this, you end up with this. And I think that's pretty credible. When you do the del squared operation, you bring down 2 powers of k, and so we've got a power of k on top here. And this is, remember that the phi star k integrated, the integral of phi star k times rho k was equal to minus epsilon delta kk primed, and so that's the number that we need in this context is that. Right? It clearly has the dimensions of an energy. So if you want to know what the expansion coefficients of a density are, you need to do this, right? This is the standard rule for expanding, for obtaining the Fourier expansion coefficients of a density. And if you plug this in and do the stuff, it comes out of this, which is simply this multiple of rho k. So what's happening here is is both simple and slightly confusing. It's that the angle action coordinates, this index k is performing a dual role. On the one hand, it's the usual k, as in k dot theta, of Fourier transforming everything into angle coordinates. But at another point, another level, it's also an index of so alpha enumerates the potential density pairs, but the potential density pairs are actually enumerated by k. So what's happened is that we've got these functions which are performing a dual role, and all kinds of things which used to be matrices are now going to be diagonal matrices. They used to be full matrices, they're now going to be diagonal matrices. So we're replacing, we're going to have A sub k's, not A sub alphas. Also, J has a dual role because it's easy to convince yourself that the frequency of an orbit is, well, it's V over L, and V is J over L, so the frequency is J over L squared. So we have all kinds of formulae in which both J and omega appear, and usually there's a non-trivial relationship between J and omega, but here the two are proportional to each other with just a trivial constant. We're going to normalize the unperturbed distribution function, which I previously had called little f naught. I'm now calling capital F in order to avoid confusion with f sub k's, because when k is naught is a possible value for k, and we don't want to confuse that with the unperturbed distribution function. So, and we're going to normalize it to unity, which means that we need to map. If we want the density, the unperturbed density, we need to multiply by the total mass. And if we want the perturbed density, we do this integral, and then we have to multiply by the total mass of the cube. And since V is J over L, this becomes a prefactor when we do the integration over actions. So the matrix K becomes diagonal in its diagonal elements. So this is the operator that enables you to solve the linearized Boltzmann equation. It was an integral over velocities of stuff, and this is what it looks like. So, so what's happening here? So obviously we're doing an integration by parts. Yes, right. And then, of course, we're doing an integration by parts, and when we do the differentiate, we integrate this one, the boundary term vanishes because stuff vanishes at infinite velocity, and then we differentiate this, bring down an ik, k drops into this, makes k squared, which cancels that, except when the i's deal with themselves, and so on. So we come down here, and this is the Fourier transform of f of j, right? Because we're taking f of j, we're multiplying by e to the I k dot j times some stuff. So it's the Fourier transform of the velocity dependence of the distribution function, evaluated as a slightly funny frequency, this frequency here. And that means that the Fredholm integral equation becomes this. This tells you the potential that is generated by the stars in the cube as a function of some the density in the cube and the potential in the cube at earlier times, T prime, but also any driving potential in the cube at earlier times. And the kernel that couples these things is this Fourier transform of the velocity dependence of the distribution function. So if we assume that we have an isothermal distribution of velocities, which you can't have in a real system because of the escape velocity problem, but in this cube we've got you can have velocities up to whatever value you like. Particles can't escape the cube, so we can have the perfect isothermal distribution, and that's what this is, normalized to density 1, mass 1, sorry, in the entire cube. Then the Fourier transform of this, since the velocity dependence of this is e to the minus b squared on 2, b to b squared on 2, we're taking the Fourier transform of a Gaussian, and so our Fourier transform is a Gaussian, and we're calling the transform variable Q. So we've got a Gaussian in Q, that's the Fourier transform of the velocity dependence of the asymptotic distribution function. We are defining the response matrix in this way, so we're saying the response matrix on the self-generated potential plus any external potential gives you the self-generated potential. And if we now plug in, we assume everything's behaving exponentially in time, we can discover what this thing is. And it's this, and it's this. So when we plug in what f tilde of q is, it's this, and then de-dimensionalize the integral. So what isn't apparent from this slide is that we're very interested in when m becomes, when m becomes 1, we can get rid of phi e and we have a self-sustaining kind of oscillation. Right? We then have the phi s is equal to m, the identity times phi s. If m in some sense gets bigger than the identity matrix, then we will have exponential growth in the absence of external driving. If m is less than 1, then we need external driving to sustain our oscillation of our system. So we're very interested in when this thing can become 1, and that's what's been studied here. So the system is going to go unstable when m goes to 1, and the condition for m being 1 is this here, and it's quite where omega is the frequency of the oscillation, and it's quite easy to persuade yourself that this term can only make this integral smaller. So usually this right-hand side is less than 1. When I say, okay, so I should have talked about the physics. So when we got these particles in a box. If the temperature is very high, then gravity will be unimportant. It will just be like putting some air in a box. The pressure in the air is way too strong to allow the self-gravity to move the air, to punch the air in any way. As you drop the temperature, which means as you increase beta, because beta is running with temperature, gravity will eventually become more important. And then it's reasonable to expect that there's a critical value of the temperature at which the mean field solution is no longer homogeneous, but you find that there's an enhanced density somewhere in the cube. You now have a sort of genuine cluster of some sort. So what we're looking for is what is the value of beta, the critical value of beta, at which the homogeneous solution goes away, and then we're going to discuss the dynamics of the system when the temperature is too high for it to cluster, and whether there still is a homogeneous solution, but it will have strange, will have different dynamical properties because gravity is playing a role. So that's what we're interested in. So if beta is temperature is very high, beta is small, and this number is small, and evidently no frequency can make this integral big enough to compensate for the smallness of this. Then as beta rises because the temperature falls, there comes a point at which, for some frequency, omega prime, this integral becomes big enough to compensate for whatever the size of this is, and so that this whole right-hand side is equal to 1. That's the name of the game. So what we're asking ourselves is, what value of omega makes this integral largest? And it's not hard to persuade yourself that the omega prime equals 0 is when this integral is largest. Or you could integrate it numerically if you like. And when it's 0, then of course this integral is straightforward. It's something like a half, because we can just integrate it straight away, and that leads to the conclusion that the value of beta for which the system first becomes unstable, satisfies this equation here. So we have the gene's temperature, which is 1 over the critical thing, which is this, and also, sorry, the other thing is we obviously put k equal to its smallest allowed value, which is going to be 1, if we're trying to make this right-hand side as big as we can. So hence this. So this is the derivation of the gene's temperature of the system. This is the temperature below which you don't expect the system to be homogeneous, and above which you do expect it to be homogeneous. So now let's work out dynamical friction. Let's drag a particle of mass mp through the cube at a steady speed, jp, the speed, the action variable of the particle, divided by L, because remember J over L, curly L, stripped L, is velocity. So what is the density associated with a point particle? Well, it's this. It's the mass of the particle over the box dimension, as it were, times a delta function. So it's nothing unless theta is equal to jpt over L squared, right? So what does that say? That is that's vt over L. In other words, this is the position at time t of the particle. So divided by L, which gives you the angle variable associated with the particle. So the particle is at this location, and we have no density unless theta is equal to this value. And if you integrate this up, d theta, d cube theta, to get the mass of this dense distribution, you need this L cubed on the bottom in order to make sure that the mass that comes out is indeed the mass of the particle. So if we Fourier transform this, we find that the so if we Fourier transform this and divide by k squared, then we will get the potential associated with this point particle, which is this. Right? So this is just we just Fourier transform this and divide by k squared as with our previous formula, we get the potential that the point particle generates. Now we calculate the response density, so that's phi sub s to the driving. We've seen this formula before. We've seen this before. So what we've got is the prefactor here. This combination of operators which we have from here, basically, right? So we have phi s 1 minus m is equal to m times the driving force. So phi s is equal to the inverse of 1 minus m times the driving force, and that's what we've got. That's what this is. So this gives us the potential that is caused by this driving potential, bearing in mind that the matter, the other general distribution of stars in the cube is caused to cluster by the driving thingy. So this is taking into account the self-gravity of the cube. And then what is mk of omega? Well, I wrote down a formula, but it involved an integral which became trivial in the event that omega prime was naught. So we have this integral. If you work out this, you can work out this integral in the case that omega prime is not naught, which is what we now need in terms of Gaussian integrals. So if you work this out, if you work out that integral for omega prime not naught, this is what you get. So here is the Gaussian integral, and then we have sort of the Gaussian thing here. So what we want is for the drag, we want to work out the acceleration or deceleration of our particle, which by Hamilton's equation is given by gradient of, since dp is more or less jp, Hamilton's equation says that it's the gradient of phi s with respect to theta. Here we have an expression for phi s, so we work it out, and it comes to this. We're looking at just the imaginary part, basically, of this, because what happens when we differentiate is we bring down a k, and then we're summing over k. We're summing over k, and so we're going to be getting, and we bring down an I as well, so we're going to be getting the complex number minus, we're going to be getting a complex number minus its complex conjugate, and that gives us twice the imaginary part of the complex number. That's how that arises. It's as a result of this k here, which causes it to change sign, and I always say here is the sum of the k grows to not k. So what does that give you? So when you work that out, here is the deceleration. Here is speed. This is the speed of the particle that we're dragging through the cube divided by the square root of beta. Well, beta is essentially 1 over the square of the thermal speed. So basically, this is the ratio of of the speed of the particle to the thermal speed. I think this probably should be a time. It's not a slash. Okay, so here we have particles which are moving, we're dragging it about the thermal speed. Here we're dragging it faster than thermal speed, and here we're dragging it slower than thermal speed. And we've got two lots of curves. We've got these curves for temperature that's very close to the G's temperature. So gravity, self-gravity of the cube is very important. And we've got these curves for a higher temperature, when the temperature of the cube is twice the G's temperature. So what do you discover? What you discover is that at and the dotted lines are what you get if you neglect the self-gravity of the cube. So when we're at this higher temperature, you can nearly neglect the self-gravity is not terribly important. When we're at the lower temperature, self-gravity is incredibly important, but only at rather small, only below the thermal velocity. It's quite striking that above the thermal velocity, you see that the dash curves in both cases coincide almost perfectly with the full curve, which means that the particles that are, if you drag your particle fast in the thermal speed, you can completely safely neglect the self-gravity. But if you're dragging it more slowly, it has a modest effect at this sort of temperature. It can have a huge effect at this kind of temperature, but this is a logarithmic scale. So, contour plots, this is for the high temperature case, twice the fused temperature. This is these are XY plots. So this is showing you the density, these are contours, the stellar density. Your particle is here, and your particle is here. It's contours of stellar density that you generate. In this case, when you're going here, yes, it should be even over, indeed. When your speed divided by the thermal velocity is 0.1, this is what you get. When it's 1, this is what you get. So when you go fast, not surprisingly, the weight is more behind you than when you go slowly, and what's shown here is what you get if you neglect self-gravity in these two cases. So these are equivalent, except here we haven't neglected the self-gravity of the cube, here we have. And this is the situation at a temperature of 1.2, so that's not the other temperature that I plotted, that was 1.05, but at a lower temperature, you can see that there's a much bigger difference in the density, depending on whether you include or neglect self-gravity, even though when we're going at this faster speed, so here we're going, here's another number, this is 0.35, so your velocity is 0.35 of the thermal velocity, here it's 0.06 of the thermal velocity. I shouldn't be using precisely these examples, but it's right. Okay, so that's dynamical friction. We can also work out the diffusion coefficients. And do you remember that a crucial diffusion coefficients very much depended on this animal here, which is basically the angular action representation of p minus 1, where p is 1 minus n. So in this case, it's very easy to work out what this is, because P is a diagonal matrix, because n is a diagonal matrix, and therefore the inverse of P is simply 1 over 1 minus the eigenvalue of n. So this inverse operation becomes just ordinary division. And this, which was a proper matrix, has become diagonal itself. And on top, we've just got these two things multiplied together. And they pretty much have, the modulus of these things, these basis functions, is pretty much 1, and so we end up with this very simple expression. So now the first order diffusion coefficient is this, and the second order diffusion coefficient is a bit more complicated because it's a vectorial thing, but it becomes this.
So do you think these expressions could give a reasonable approximation if I use them for a galaxy, like maybe in the middle where it's uniform, or not at all?
Well, I think that is sort of the question. Which I'll say. So the point is that the self-gravity is only important on the larger scales or system scales. So here that represents the case of k about 1, k having been a vector with small integers in it.
So it's the
in the case of a galaxy, you can't any longer think of it as being homogeneous. So your idea obviously is that I'm inside this hot galaxy, and in some small volume, it's homogeneous. Exactly. Within that small volume, the self-gravity is that the particles are moving so fast, the self-gravity is not going to be important. It becomes important on the scale of the system. And so unfortunately, you can't sort of apply these formulae. They're just, it is only a toy.
Okay. So the diffusion coefficients really depend on, like, if I take a elliptical galaxy and then a similar one but just twice the size, the diffusion coefficients would be different in the middle.
That's well.
Like, because on one hand I understand
Yeah.
that gravity is long range. On the other hand, it's not very intuitive that it should make a difference. But maybe.
Well, what I think, as I'll say briefly later, the current understanding is that it doesn't make a difference to the diffusion coefficients, because we do get large amplitude fluctuations on large scales through this apparatus, but they happen so very slowly that nobody can. Well, the number of stars that can resonate with them is very small.
Exactly. So if I have a time scale of some sort, can I use the periodic cube and say? You see what I mean? Like, when is too slow so that I can neglect it. So if I know this.
Yeah. Well, in the case of the periodic cube, it turns out we will find there are enormous enhancements in the diffusion coefficient, and that is telling us that these system scale oscillations don't happen so much more slowly. It happen on a time scale which a significant number of stars can respond to. Whereas it seems, from the study of the isochrones system, that isn't the case in, say, the isochrone system.
And for the dressing, it is the same story, or like, can I imagine the dressing of a star in an elliptical galaxy similar to the plots you showed before, or is it also very different?
I haven't seen that. Somebody's got first. Let's just. So what do the results look like numerically? Okay, so what we're seeing here is, again, your speed relative to the thermal speed. And here are diffusion coefficients parallel. So I didn't. So D2, the second order diffusion coefficients, form a matrix. This matrix obviously is symmetric, so it can be characterized by its eigenvalues. And if you're in an isotropic system, if you're in a system where the velocity distribution is isotropic, then there is only one naturally defined direction, which is the velocity at which you're asking what is the diffusion coefficient of this velocity. So the system has symmetry such that two of the eigenvalues have to be equal, and there's an independent one. So these are the parallel and perpendicular diffusion coefficient. So D parallel is the rate of diffusion in the direction of your velocity. It's the expectation per unit time of the component of change velocity in the direction of your current velocity, and the perpendicular is correspondingly the expectation of unit time of the square of the change of velocity perpendicular to your current velocity. So, and they behave very differently as a function of speed. So if you ask, the perpendicular diffusion coefficient at high speeds is enormously larger than the parallel one. Now, why have we got, so this is the perpendicular, this is the parallel, and this is the drag coefficient times a factor of 10, so just so that it appears clearly. And why do we have all these curves? We have all these curves because our formulae deliver these animals as divergent sums over k. So, sorry, how can I persuade you that that's the case? I'm sure I can. Should be able to. Well, the number of k's, the number of k's rises like k squared to k. So if we look at this, the amplitude, basically the factor here is 1 over k, and then we're going to be multiplying by k squared to k to a high k, we're going to replace this somewhere by an integral, k squared to k, and so you can see we're going to be having something which is strongly divergent. Similarly here, this is behaving like 1 over k cubed, I guess, because we've got a k squared on top and a k to the fifth on the bottom. So when we multiply by k squared to k, we get a logarithmic divergence. So what's that saying is that this apparatus is giving us large results coming from the sum of very small scale effects, because high k means small scale effects. And that's why, so I plotted these curves for when we have 2, 4, we sum up to modulus of k is 2, 4, 6, 8, blah, blah, 64, right? And you can see there's no sign of convergence. Indeed, there is no sign of convergence. So what do we do about this? What we do about this is say that this apparatus is good for discussing the system scale fluctuations, but it's not good for discussing the very large scale fluctuations, very small scale fluctuations, basically because if we come very close to another star, we're going to be deflected through a large angle, like here, and the apparatus that we're using is obtaining the change, shall we say, in the perpendicular component of velocity by integrating the forces along this unperturbed trajectory. So when the trajectories are on very small scales, the trajectories can be significantly deflected, and then this perturbation theory doesn't work. So what do? What we do is add in the classical Chandrasekhar calculation. So the standard thing is this is a Kepler orbit. It allows us to calculate exactly what the change in the perpendicular and parallel components of velocity are, and then we add those up over all possible impact parameters b. And when here we're working out the change in the square of the velocity. So in delta v over time delta t squared, you get something like this, where the sum over impact parameters, so we have a certain flux of stars, a certain number of stars come at speed v and impact parameter v, and we need to sum those, and we end up with a sum that looks like this, which is logarithmically divergent now with very large impact parameters, right? Because this v90 is the small impact parameter at which you get a 90-degree deflection. So when b is large, this integrand is looking like 1 over b, so it's logarithmically divergent. And that divergence is traditionally just packed into a factor log lambda in the formula, for which you don't have any reliable value. And you can work out what the diffusion coefficients are. This is just one part of the diffusion curve, one part of the diffusion curve. It's the trace really of this thing here. You can work out what the whole thing is with some considerable amount of with some considerable blood, sweat, and tears, you can work out what this apparatus predicts for the parallel and perpendicular eigenvalues of the diffusion tensor, and you have this stuff, these various integrals over exponentials, etc. This is all, you can find this theory goes back to Chandrasekhar. It can be found in the appendix of Galactic Dynamics. And what do you get? So what you want to do is say the cube does the large scales correctly with this discrete sum, but it isn't practical to sum up to, sorry, does the large scales correctly. And as delivering the answer as a sum over k. You don't want to do this sum over k to all k, because you can see that you're going to get a divergent result, and you will understand why you're getting a divergent result. It's because we're doing first order perturbation theory, and we're not able to cope with large angle deflections. The Chandrasekhar apparatus, based on Kepler orbits, does the small scale stuff perfectly because it deals with large deflection angles, because it's using the Kepler formula, etc., but it can't cope with large scales because it assumes that the asymptotic trajectory in and out is a straight line, and it assumes that the density of stars is independent of location. So it's clear what you should do. You should do the sum up to k max, which gives you a characteristic impact parameter 2 pi over k max, and then you should use Chandrasekhar's apparatus integrating up to b, which is 2 pi over k max, and these diagrams show that it doesn't matter at what point. So all being well, it won't matter up to what k max I go. I go up to some k max that's sufficiently large that I've gathered in all the effects of self-gravity, all the things that require to be thinking on a large scale, and then I can transfer to the rest of the sum of the sum using Chandrasekhar's apparatus, and I simply make sure that I match the maximum impact parameter that I take in Chandrasekhar's apparatus to the maximum value of k that I use in the periodic cube apparatus. And basically, these diagrams are showing that the local scattering approximation and the periodic cube match perfectly. So this is the dynamical friction coefficient. This is the parallel and perpendicular components of the. Sorry, what is plotting is, excuse me. This is plotting the derivative. So log lambda. If I take away this log lambda, I am getting the coefficient of log lambda in this expansion. I'm discovering how fast the result varies with my upper impact parameter. And you can show that ought to be the same as the rate at which the periodic cube results vary as you vary k max. As I increase k max, I'm including a few more impacts, and I would like that to, I would hope that would agree with what happens when I increase log lambda, which means I get a few more impacts of the characteristic scale. And the red and the black curves are very, very similar at all velocities when I do this matching at some value of k max. And you can convince yourself that if you change the value of k max and at which you do this experiment, you get that within some wide range, there remains good agreement. Here, the agreement is essentially perfect. So here I'm showing for the temperature is 1.2 times the G's temperature. The result of summing up to k max is 64, and then taking the local approximation with a particular value of log lambda, which is log lambda gives me the ratio B max over B90, which corresponds to 2 pi over k max. And this is the complete dependence of the So what I was showing you before was derivatives. Now I'm showing you the actual drag. This is speed. And if you just use the Chandrasekhar apparatus, this is what you get. And if you use this complete apparatus, this is what you get. And doing the same thing for the diffusion coefficients. Here is the parallel diffusion coefficient. Here is the perpendicular diffusion coefficient. And this is what you get. This again is 1.2 times G's temperature. This is the diffusion coefficient that you get, diffusion coefficients that you get if you just use the Chandrasekhar apparatus. So you can see that at this kind of fairly low temperature, the Chandrasekhar apparatus is horrendously underestimating the perpendicular diffusion coefficient. Okay, so that suggests that you really should be worried about Chandrasekhar calculation. It's inherently unsatisfactory because it always involves this log lambda term, and there isn't ordinarily, without this apparatus, you've got no convincing way of saying what log lambda should be. Now, in that case, the periodic cube, I'm demonstrating that you can take log lambda to be anything you like within reason, and you just need to stop when you're still on fairly small scales, and then hand it over to the periodic cube calculation, because the periodic cube calculation does the large scales well, the Chandra calculation does the small scales well, and they can be matched essentially perfectly. So, recently, Peterson and company, that's Peterson, Fowler, some other people, Hamilton, studied the isochrone cluster in a similar way, but not quite the same thing. So they computed this object E that I talked about, which is this matrix E, which is the key to determining the diffusion coefficients for an isochrone cluster summing to very high values of K, with and without self-gravity. So I'm actually unclear. So the periodic cube tells you that you mustn't sum to arbitrarily high K. You have to stop at some finite K because the apparatus gives you divergent results. And I'm actually not clear what they did about that. But anyway, what they did was they did this summation to pretty high K, including the effect of self-gravity. That's when having n not equal to 0, and when self-gravity was left out, that's when n equals 0. So they were probing how important is self-gravity, and their conclusion was that the effect of self-gravity was actually modest, and in fact, remarkably, dynamical friction was actually reduced by including self-gravity, which is a result that Martin Weinberg found empirically in simulations a long time ago. The argument there, or the reason why that's supposed to happen, is that there are two things involved in generating dynamical friction. One is you need to have a wake, you need to enhance the density around you. The other thing is it needs to be behind you. And the argument is that the reason that self-gravity reduces the drag is that even though it does increase your wake, it puts you more nearly in the middle of your wake, so you don't feel as much of a drag. That, I think, is pretty much what I wanted to say today. This is a little calculation. For the periodic cube, this is the distribution function of a normal mode. And if we integrate over J, over velocity space, it needs a bit of density, we can express it like this, and we can discuss the dressing of the mode in the following way. The thing that's on the right-hand side is essentially the gravitational potential produced by the resonant stars associated with the mode, that drive the mode, that characterize the mode. And what we have on the left is this is the complete potential. And so dressing manifests itself in this number here being less than 1, so that the actual potential is equal to the bare potential generated by the stars that make the node, divided by this number which is less than 1. And if you simplify, if you put in an isothermal distribution function, this parallel thing is the unperturbed distribution function integrated over velocities perpendicular to the mode wave number. So if you put in for an isothermal what all this is, it reduces down to this. This left-hand side becomes this here, and this integral I'm plotting here. So it depends on x0, which is basically what this is, since this is 1 over the thermal velocity. This is basically the crossing time. It's the frequency of the mode times the crossing time. So we'd expect it to be our number on the order of, well, it's whatever you like, because we know there are modes at every frequency, but we expect something interesting to happen when this is a number on the order of 1. Anyway, x0 is what I'm plotting here, and then this is the value of this integral. And so this integral, we're interested in the case sorry, it's minus this integral. So we're interested in the case where I think I should have had this minus sign here. No, I should have had this minus sign here. So at low frequencies, we expect, so when x0, no, that's right. Anyway, I'm interested in the case where this, I think I have plotted in mind, got the minus sign wrong, I'm plotting, bother. See, df by dj is negative. Df by dj is negative, that's the origin of that minus sign. And then, so this formula is correct. And how do we think this integral varies? When x0 is very small, we would expect the integral to be positive, would we not? Because, so it's negative until x is equal to x0, and then it's positive. So I must be plotting, I'm afraid, minus the right thing. So we turn this thing upside down. It goes from -1 to 1, so it should go down like this. So when x0 is small, this thing is a number which is on the order of 1, but not 1, and it actually passes through 0 at 0.4 here. And that is a measure of how much the mode is dressed. It's telling you that low frequency nodes are positively dressed at this number less than 1, but high frequency nodes are negatively dressed. This number is actually you get less potential than you put in, which somewhat surprised me. Well, thank you for the patience. I found it a very useful exercise to have to articulate this, and you will notice that there are many things that I seem not yet to understand, and this is definitely true. And I've got a great deal of cleaning up to do, but thank you.
Thanks. I think this was great.
Questions or anything? Yeah.